Anyone working with Databricks currently? OK, nice, good. So yeah, I'm not going to do too much of the intro, this is what it is kind of thing, because hopefully that's kind of been covered. I'm going to dive into why we use it, so what are the really good benefits of doing it, and just some examples of some horrible, dirty code that I've written that will actually help the way you're doing things. Objective is not to teach you exactly the code that you need to put in, but more to, I guess, say this is how you can use it to really benefit what you do. It's kind of the plan. Am I meant to have started yet? Good or best? Good to go? Cool. Hi. So my name's Simon Whiteley. I work for this company, Advancing Analytics. We are a analytics consultancy, shockingly enough. And we do lots of this kind of thing. We do all Microsoft, all analytics, all Azure. So working with lots of data lakes, working with Databricks a lot, SQL Data Warehouse, Data Factory, that kind of, how do I go from doing BI and things on a SQL server to actually doing it as a distributed cloud system, using unstructured data, using huge, massive data volumes. It's like it's a whole shift in terms of how you think about things, how you approach things. That's what we do. As always, sponsors, thank you to sponsors for paying for this, for, again, food, drinks, running a conference, it's expensive. So putting this kind of thing on to make sure you guys can actually come and learn stuff. Thank you to all of them. Slides are on GitHub. So I'll share the slides anyway. But if you want to have a look, you can grab a PDF of them on there. And there's one of the demo notebooks is on there as well. So again, feel free to grab a photo, go onto that. And they might be slightly different because I've been tinkering and changing the slides during Andre's session. So this is updated. And this session is, let's just say, fresh. Because we're having a look at the schedule and realized that both mine and Andre's sessions were very similar. Both that kind of gentle intro to Databricks, get you started. And I was like, well, since I'm going straight afterwards, why don't I just do a little bit deeper, make it a more advanced session. But I didn't have one ready, so this was written largely yesterday and today. So I have no idea how long it takes. So we'll just see how far we go. I've added a load of extra stuff based on some questions that were asked, and we'll just see how we do. Sound good? If there's any questions, anything you want to know about, feel free to just ask as we go, and I'll see what I can do to try and include it. And then we'll see what we get through in the time. Sound good? Grand. All right. This is the main plan. We're talking about schemas and inference. That whole idea of, because I'm dealing with big data, one of the big problems with big data is it's unstructured data. One of the big misnomers about a lake is it's this terrifying thing with no structure. And that's a lie. But how do you make sure it has structure? How do you do ETL? How do you validate data's in the right shape, which is one of the classic problems? So looking at schemas, looking at validating data, we'll have a little bit of a look at orchestration. Because if you just do it via the Databricks jobs, then that's kind of just within Databricks. It's like using the SQL agent to do your entire end-to-end ETL, whereas we've got things like Data Factory that can talk to lots of stuff. And then I've got a ton of slides on Spark internals and how the engine works and RDDs and loads of stuff. And essentially, we'll just see how much we get of that. The main things, the top three, to give you that. How do you use it for ETL? How do you use it to solve the classic problem of speeding up ETL? OK? Good. So I've got a few slides just to put it in context to explain it. I don't want to just throw a load of code at you without context. So we'll go through some ideas, some stuff to kind of lay some groundwork, and then we'll get on some demos. So this is the why. This is what is Databricks in context to what we do to our analytics for BI. Because so often you have that end piece. I am doing BI, therefore I spin up a SQL server, I make my stage clean warehouse database, I do some Kimball, I get SSIS and pull it out and do some transformations and all of that stuff. And things are getting quicker. People want to do stuff in a more ad hoc way. People want to try and respond to new opportunities, to challenges, to issues far, far quicker. And so people are starting to use data lakes. People are starting to get that message that, having something without formal structure so that I can respond quickly is a good thing. And that idea of that so certainly that raw layer, is basically just a glorified staging area. It's saying, actually, someone says, can you start capturing this data? And in the old days, I'd have to go, well, I'll need to design a staging table, and then an ingestion pipeline, then I need to test it, and then regression test it, and add to my master schedule, and then deploy it. And the answer is yes, but in 2 months when my next release window comes. Whereas if you're working with a lake, and it's a case of, sure, just dump it in a folder, and I'll get around to cleaning it up. It's not quite that simple. You need to obviously design your folder structure and have some rules and regulation. But it is as easy as just start landing it. Start capturing data, think about what you're doing with it later. And that is kind of this whole revolution of how we're thinking about data. So the early part, capture data, deal with it in an automated way, is really speeding up how we react. That's kind of why we're doing it, why we're working with data lakes. And that kind of transformation, if we've got data in the lake, how do we pick it up and work with it? How do we transform it? How do we do things like cleaning the data and joining data sets together? Databricks is our answer. That is the compute that we use on data that's in the lake. So that's positioning for me. So it's not saying this is now your warehouse. It's not saying get rid of SQL Server, Databricks is here. You can do, but let's not go there. It's saying it's another tool you can build into your arsenal to allow you to be more agile, more flexible, and do things in a better way. So, a little bit of dirty inside stuff just to put things in context. I'm not going to spend too long in here. We can go back to this later. So, Spark Engine. You've got the actual main core engine, the actual application, written 80% of it written in Scala, which is a Java-based language. It's written in Java. So it's kind of hugely Java-based. And it's doing this whole thing of MapReduce. It's the whole idea, lots of things in parallel, split a job up amongst several workers, get them to churn through it and work with it. And the way it does that is via that next level up, that thing called an RDD. So that is a resilient distributed data set. It's quite hard to say, I've had to practice. So essentially, anytime you get some data, anytime you have a table of data and you bring it into memory, into context in your Spark cluster, it breaks that data up into small in-memory chunks of data and then spreads them out across your workspace, all the different workers that you've got in that cluster. Okay, so everything, absolutely everything in Spark happens at that RDD layer. And the RDD layer is hard. It's quite complicated to work with. And back in the day, that's what Spark was. If you're working in Spark, then you were doing everything at the RDD layer. And it's like, so as an example, if you want to do a count, that kind of select count star kind of thing, build an iterator. You have to build the logic to go, loop through my RDD, get an iterator, increment it. You have to manually code that. There's no like do a quick join and things. There's a lot of manual coding to work at the RDD layer. And that's all Scala-based. You can write Python there, but it performs awfully because it has to push it outside of the Java virtual machine. So if you talk to anyone who's like an old school Spark guy, and you go, hey, I'm using Python, they'll go, you idiot, it's not going to perform, it's terrible, you can't be a Spark dev writing Python or R or SQL, you have to use Scala. And that's because back in the day, everything was RDD. These days, the Spark engine itself has evolved, there's so much more stuff into it. So you've got this thing called data frames. So examples we were looking at earlier, that data frame is an abstraction on top of RDDs. It's a whole lot of things to be able to make it behave like a table. So you can write things like group by and joined and all the kind of the SQL abstractions we're used to. And that all works. What it actually does, it takes that and it turns into RDD commands, so we don't have to. So again, everything still works at RDDs, but it means if I write Python against a data frame, it's going to turn it into Java and run it on RDDs. If I write Scala or R or SQL, it actually does the same thing under the hood. So if you're working at the data frame API, it doesn't matter whether you do Python or Scala or SQL or R, it does the same thing. So if anyone tries to bat you down and say you're not allowed to write Python, you are because it's changed. Work with the data frame and you're happy. Okay? A little bit of context. That's why it's okay to use it these days. Don't believe the internet, because obviously the internet's full of years worth of Spark stuff, which didn't used to work that way. Cool, right, onwards. So we saw a data frame. And there's a couple of key things inside that data frame as to what it is. So we've got a schema. Then this is the shape I'm expecting this data to be in. We've got a format. Is it CSV? Is it JSON? Is it Parquet? Is it Avro? Is it some other type of data? Is it an image file? You've got a location. Where do I go and find it? So when you're creating that data frame object, kind of like a table variable-ish, it's essentially some metadata that describes where to go and find that data. But you can give it, in that case, variables. So I'm passing in, at runtime, this is what the structure should be, this is the format, and this is the location. And that makes it massively flexible. So actually, I can just insert those as parameters. So we suddenly realize that unlike the old days when I'm saying this is a SQL table, and this one table is for this one structure of data, I'm now saying, well, this object, it could be any bit of data with any structure in any location in my lake. I can write a generic script that does the same set of transformations, the same stuff, on different data frames depending on what I pass into it. And that's kind of like completely different way of working. So some of the examples I'm going to go into is like, how do you do that? How do you work with the same transformations for different stuff, which then just has massive implications for automation? Don't build a new script for every single data set. Build a single script that works on any data set you give it, and suddenly you're not having to do deployments. There's no deploy, testing, these stuff. It just adds some metadata, and then the next one, it just start running. So your ability to respond is just huge, huge things if you're doing this properly. All right, so some structure. We saw briefly you can do these infer schema things. So I've got a CSV. The CSV doesn't really have a structure. It's kind of semi-structured. But I can tell Spark and tell Databricks, I want you to read the header, read the first line and just work out what the column names are, and then infer the schema. And the same way you did with SSIS, where you can say do a sample and it'll read the first 100 rows, and then it'll kind of work out your metadata for you. This does a similar thing. So I can just throw it at a CSV that it's never seen before, and it'll go, you know what, that's the structure. Based on sampling, it's got a string, it's got datetime, a string, int, that kind of stuff. So it can go off and work out structure for you. However, a lot of what the data frames are, you're rarely looking at a single file. And that's a weird thing to get used to. So often we're saying this data frame is this folder and all subfolders and all files in there. So a data frame can have tens of thousands of files in there. And then when you query it, it acts like a single data set. And that's like massively powerful because you'll be throwing new files in there, and then you'll see that as part of your data frame. That's great. If you're using infer schema, it does a sample of every single file. So suddenly, going from infer schema, great, really flexible, just works out what the structure is, it just absolutely tanks performance. So using infer schema, we don't do in production. Okay? Good. There's some patterns you can use to get around it. So one I see quite a lot is, well, actually, the schema is an object. So I've got a data frame, and I say, infer my schema by looking at this file, and that'll create that little structure. So here are the headers, here are the different data types. And I can say, well, just take that structure and apply it to my other data frame. And that's much faster, because I've only done the inference off one single file, and then just apply it to everything. But then I'm relying on that sample file actually being right, being representative. Maybe that sample file, the data's kind of changed a bit, and things are going wrong, and it's, yeah, you can do that. That's a quick pattern, but it's kind of a dirty hack. So, yeah. What people tend to do is keep metadata. So how you kind of work with structures is you abstract that problem and say, well, I'm going to keep my expected structures for all these things. You can put it in a SQL database, you can put it in Hive. So Hive is very common in the big data world, essentially makes things that look like tables, which are just pointers to things in the lake, essentially a whole collection of metadata describing what your lake looks like. You can just have JSON files sitting in blob storage that just describe your files. Essentially, take your metadata, store it somewhere, and then you can use that saying, I'm trying to read this data set, what should it look like, and then bring the two together. Okay, so that's quite a common problem when you're first starting to work with a lake. Get your metadata, put it somewhere. Simple as that. Okay. Hive, you've got a couple of options. Hive is baked into Databricks. So without you doing anything, if you're working in the SQL layer, what Andre did, is you can just do save as table. And then it appears as a SQL table. That's actually using Hive. That's writing the metadata to an internal Hive store. Now you can go and write it elsewhere, and it depends. Do you want to, just within all clusters inside your Databricks workspace, have that shared? Or do you want to share it in between lots of different Databricks workspaces? And you've got that choice. So you can set up an external one if you want to share it across workspaces. But generally, you just turn a cluster on and then do save as table. Then that's going to remember that, and people can use it. And that's pointing at some metadata about the lake. Okay? So metadata is a concern. You need to think about how you're going to do it. Cool. One rant. Rant number two, partitioning. So we mentioned that you don't have an index. It's not a SQL table. You can't say, select where my month is 3, and expect it to know what's in each of those different CSV files. Because as far as I know, that is just a file of data. It's got no B-tree index on the top to go, well, this file contains this data. It's got no information. If you're just pointing at a single massive CSV file, it has to read the entire thing and then go, oh yeah, that's not what I wanted. You know, it'll pull it all into memory across all your executors and then filter it down. So you're just reading everything and then deciding later. Now you can partition. So there's no indexes, but there is definitely partitioning, and you should use partitioning. Partitioning will happen automatically if you're using Hive syntax. So those folders, I've named them month equals whatever, attribute equals value. That is Hive syntax for saying, well, this is a partition. So inside that, I'll point my data frame. This is going to work. Whoop. I'll put my data frame at that top level, at that sales folder, and it's automatically going to read everything in there. And because it sees those subfolders with that syntax of attribute equals value, it knows that's a partition. It adds that as a virtual column. So even if my data didn't have month in there, I start opening my data frame, I look at the structure, and it'll say month. And I can say, well, query where the month equals 3, and it will automatically go, well, I don't need to read the other files. So you can do partition elimination just by naming your folders properly. It's a big thing to get that. So lakes have structure. Getting the structure into your head and getting that structure as to planning how you're laying data down can massively impact performance. Because not only for just the reading of data, but even the checking access. If you're using Data Lake Store Gen 2, it's using ETLs. It has to go, do I have access to this file, access to this file, access to this file, access to this file? If it's doing partition elimination, it's not even going to bother reading what files are in those folders. It's going to go, I don't need to worry about those. So even just from a pure access check, it speeds things up. So partitioning is good. If you can partition your data, lay it down like that, you can have multiple levels. So year equals, month equals, day equals, and it will automatically bring those all in and it will work out how they work. So it's cool. And you don't need to do anything. You don't need to set that in your data frame. It's just, it will automatically pick that up. Yeah.
Is that directory naming?
That's directory naming. So let's actually just, why don't I show you? So if I go in my lake, inside my base, inside public, I think. Got some taxes. Okay, so pickup year equals 2017. So it's going to automatically know that there's a year, pickup month, and then if I did a query saying select star from my data frame and pickup month is 3, it would only read the files in there. So yeah, absolutely, directory naming within the lake will partition for you. Okay? Cool. If we've got time at the end, I can show you a demo of how you can tell it's done partitioning, but I don't think we'll have time. Okay.
Can I just ask on that, can you do the partitioning manually or externally to Databricks?
Yeah, it's whatever you name the folder. There's no extra stuff in there. So if you're using Hive and using deep Hive stuff, then yes, you need to tell Hive to go reread things. But if you're just writing the data frame manually, it'll inspect the folders and just go, oh, there's partitions there. Okay? So you can have Data Factory landing the data and just code it into Data Factory to say, just add the current day as a folder structure. Cool. Okay, so partitioning. So validation. So we've said we can apply a structure. So I'm giving those two things. I'm saying I want a data frame. It's pointing at this CSV in my lake. It should use this structure. So I'm saying my structure is 3 columns, one of them's string, integer string. This is what I'm expecting. And then the data comes in, and it's wrong. So what happens then? And there's a few different ways we can deal with it. And that, the most common ETL problem of all, right, is I've got the wrong data type. This isn't what I expected. There's an extra column in my CSV that's a comma that shouldn't be there. So our example data in this case, row 1's fine, row 2, the middle column, that should be an int, it's not. And row 3, I've got an extra column. So what happens? So in our data frame, we've got a couple of options telling it how to handle this stuff. So we can say, be permissive. Just basically allow it through, don't error. Any of those rows that fail to pass, it'll just null out everything, which isn't great. And any extra columns, it'll just ignore. But that's kind of like just don't break, that's fine. You can fail fast. So as soon as one thing fails, just break. Don't bother spending an hour getting to the end of the other 100 million rows. Just break as soon as I physically can. Or the head in the sand approach of drop malformed. Get rid of the things that don't work. Only return my one row. I don't want you to error, but just throw the other stuff away. I don't care. And again, none of those are really good ETL options, right? If you have ETL and just randomly leaking data, that's not exactly the way forward. So there is a better way. So let's take a bit of a look. Okay. So over in Databricks, I've got my workbook here. Let's just do option 1, really quick. So I've got my structure. So in this case, I'm giving it the structure manually. So I've hard-coded the structure. This is what I'm expecting to see. Got a data frame. I'm saying read it. Use this option, option permissive. Option permissive is also the default way. So if you don't give it an option, this is how it'll work. So this is going to say, if there's anything that doesn't work, null out that column or just ignore the extra stuff, but otherwise just don't error. It'll be fine. I'm feeding that schema into it. So I'm saying this is the structure to use, and I'm giving it a place in my lake. Then I'm just displaying that. I'm saying, well, what's actually in that data frame? And then I see some data, and if I'm missing any columns, I don't know. I can't see. And there's a row in there that's all nulls, but I don't know where it is. But that's not great, and I can see I've got, what, 280 rows on that. So fine, it's OK, but I'm losing data. Fail fast. So this will work. So I've defined my data frame. I've said use fail fast, and it goes, tick, OK. Because Spark is lazy. And this is a real weird thing to get your head around. You can keep lining up commands. I could say do some transformation, join these tables together, and I can keep just issuing transformations, and it'll take a couple of milliseconds to go, OK, sure. OK. And it's only when you try and write the data or display the data, only when it actually has to read the data will it do it. So each time you're running a command, it's essentially just building up a list of the transformations that it should do. So defining the data frame works. As soon as I say display the data frame, I get an error. So it's now going to break. So it's malformed records detected, and I'm using fail fast. So it's errored nice and quickly, but it's only errored when I've tried to see the data. Again, not great. It's broken. That's not great ETL either. Going down a bit further. Again, if I do a count, I can't do a count because that won't pass. Drop malformed, similar stuff. Just works. My data works. It says nothing's wrong. Life's good. But actually, I've lost data. So if I try and have a look at what my data looks like, so we can do a count. If I do a straight count, it says 280. Anyone know why? OK. So record counts, it doesn't need to have worked out if it fit the columns. It can just go, well, I can just count the rows and tell me that. So it actually isn't trying to parse that schema. If I do a cache and say, well, force this into memory, remember what this structure is, and then do a count, I'm down to 274. Because I forced it to actually evaluate that schema. If I'd said display and just print out the rows, I'd have 274. So you've got to be really careful with how some of these things work. But obviously, none of that is great. So what we can do, this is the big secret. I'm going to use permissive mode again. So I'm going to say, go back to our first one. Don't throw any data away. Keep all of my rows. And actually, I'm going to lie to you. I'm going to tell you that the structure has an extra column called corrupt record. Now, that doesn't exist in my data. That is a system field that I'm saying tag that on the end. And what that does, it's going to populate that with the original row. So I can go and have a look at my data, do a select. When I get that back, right on the side, I can see the rows that had an extra column. I've got that data. I can see my top one. That's the one that nulled everything out, because actually that's NAs. There's an unknown member in there. That obviously didn't pass because it wasn't an int, and that's why I've got errors. So I can now detect in my data set which things didn't fit that structure, which things did. So I can then do a filter and just say, well, actually, just give me the ones that actually work. That's in the demo. So in the GitHub, you've got that script just as a reference to go through and see how you work with that stuff. And we're going to get a bit more advanced. It's fine. OK. So generally, good idea, ETL. It's kind of making sense how we're working with that. Yeah? Good. OK, orchestration. So we've got that notebook. We want to run that notebook on a regular basis. But actually, I don't want it to just run on the same data. I don't want to have to make one of those notebooks for every single different data set I've got. And so there's some things you can do to kind of pass information to and from a Databricks notebook. So we've got a thing called a widget. Great name. Essentially a parameter. So you can have that code, and that code is weirdly in your notebook. So at the top of your notebook, you can say, add a dbutils.widgets.text, drop-down, combo, multislate. There's a few different ones. And these will just add a parameter at the top. So if I run that code, my notebook will change, and suddenly I'll start seeing 2 parameters at the top. So inside the code of your notebook, you tell it what parameters to expect, and it'll go and build them for you. And then later in my notebook, I can refer to it and say, well, get the current value. So I can say, expect to be told the file name, and then throughout my code say, well, actually, create a new variable called file name. You get it from looking at that widget, and then all through my code, I can refer to the file name. And you can have lots and lots of those different parameters building up. So you can start to make your notebooks fairly dynamic. You can say, well, these are the things I want to know each time, and then they're inputs I can give it from an external place. Whether I'm calling this notebook from another notebook, or I'm calling it from a REST API, or I'm calling it from Data Factory. I can go and pass these parameters in. And suddenly notebooks become a lot more extensible, a lot more generic. So Data Factory, you've got a few things you can use. You can just run a notebook. So I can just point it to my Databricks instance. It'll give me a list of my folder structure of my notebooks and say, I want you to run that notebook. That'll hook up quite nicely. You can run Python scripts. You can run a jar file. So a jar file is compiled Scala, it compiles down to jar. But again, notebooks are quite nice, because notebooks, you can go and see the history of that execution. So if you're doing it as like an ETL support kind of thing, and it breaks, your support guys can click on a link in Data Factory, and it'll take them to the actual history of the run. And under each cell, they'll see, oh, that's where it failed, and it failed because the schema was wrong because we did that. So using notebooks is actually a good support mechanism for people to work with it. Okay. We saw jobs earlier. So jobs are actually used by Data Factory. It creates a job for you, executes the thing, tidies itself up. And again, you've got the choice in Data Factory. It can either use an existing cluster, so anytime I execute it, just use that cluster. And if it's already turned on, run it. If it's not turned on, start it up for me, which is great. Or you can tell it to, every time you execute, spin up its own cluster, which takes 4 or 5 minutes. And so there's no overhead each time you do it. But you make sure there's no contention. It's not going to be trying to kind of run at the same time as anything else. OK, so because we've got widgets, that's one really good thing we can do. So in Data Factory, I don't know if you can see that well. In my notebook task, I can point at a notebook. I can say, there are some parameters, and I give it the name of a parameter. And that has to be the same as the name I gave the widget. So into that one, I've got underscore entity name. Can I do a zoom? Whoop. No. OK. So I've named it entity name over there, and it's looking at the widget called entity name over there. And if they're the same, it'll pass it into that widget. So Data Factory can populate widgets for me. And this sort of thing we saw on the bottom, I've got a thing called dbutils.notebook.exit. And that will actually allow me to pass stuff back to Data Factory. So I can just fill it with a string, or I've done there, I filled it with some JSON. So in Data Factory, after my notebooks run, I can look at my output, and I'll have that little bit at the end, that kind of JSON object. So I can pass things back, like how many rows did I process? How many failed? How many succeeded? And suddenly I've got that nice two-way communication. So Data Factory can be saying, run this notebook with this parameter, receive some data back, and then I can inspect that in later Data Factory things. So I'm saying, if there were rejected rows, run this other path. If there was no rejected rows, continue and do the next thing. You've suddenly got this nice visibility between the stuff that's in there. OK, so the dirty great demo. How are we doing for time? We're OK. Cool. So this is the thing that we're trying to build. So I want a Jupyter notebook. I've got two sides to my lake. I've got a raw side. So this is the data where I'm getting data in, and it's going to be a bit dirty. It might just be CSVs, it might be JSON, it needs some cleaning up. I'm just receiving some data. Also in there, I've made sure whoever's landing data for me has landed a separate bit of JSON that just says, this is the structure to expect. OK, so two things, data set, what that data should look like. What I want my Jupyter notebook to do is to pick it up, put it in a separate area of the lake that is just for clean data, and land it as Parquet. Parquet inherently has its own structure built in. So it has some metadata inside the Parquet file, which says, these are the columns, this is the structure, this is built in. So I no longer need to worry about what the structure of that file is. That is known because it's Parquet. So I can put my valid data over there. And if there's anything that's not valid, anything in that CSV that just didn't make sense, I can just pass that onto a separate file. So normal stuff, pick up my data. Is it the right shape? The stuff that's not the right shape, reject that over there. I'm going to put a table name into my notebook. I'm going to spit out number of processed rows, number of good rows, number of bad rows. OK, classic ETL task, pick up, put down, all good. OK, so this is a beast. And again, this was written this morning, so let's see how long it takes. OK, so I've got my notebook. It's all hooked up. Do shout out if there's any bits that you can't see, and I'll make sure I am zooming and stuff. OK, so first thing first, I've got my widgets. So I've got a little bit of code saying, I want a widget here where someone can tell me the table name. So because I ran that, it means at the top I've got this thing. So I've got product category. So I'm looking at a VentureWorks table. I can just go in here and inspect what that widget is. I guess for a bit of context, I can show you Storage Explorer. So in here, in my root, I've got my raw folder. So this is all my data that's yet to be cleaned. I've got some categorization for sensitivity. I've got AdventureWorks to know where it came from. I've got a load of different tables in here. And again, this is just a straight, I got a data factory and just said, just do a loop and just dump out CSVs. So I've got a load of CSVs in here that are just whatever was in AdventureWorks. Then underneath, I've got a load of JSON files. So that's my starting point. Some folders with a CSV in it and some JSON files. I'm trying to move that into a new place. Okay, so I've got my widget. These two bits are doing just connection things. So I'm saying, I want you to go to my secret store, pull back my service principal connections. I'm telling it how to connect to the lake. Again, Andre showed you that earlier. You can find that on the internet. Basically, if I'm trying to run this unattended, I need to tell it a service principal to use. Now, you can do pass-through authentication. So I can have it so a user sitting here running it doesn't need to do that, and it will just use his AD credentials. But that doesn't work if you're using Data Factory as an unattended thing, and it only works with high concurrency clusters. So it's not really recommended for like big, chunky data processing tasks anyway. So generally, set a service principal, life is good. Okay, so I'm grabbing the current widget value. So I want a variable called file name. That's just going to get whatever I've got in that top, in that parameter, populate that variable file name for me. I've then got a dirty load of JSON. Okay, so there's a few things here. So I'm giving it a base schema location. I'm telling it where to find those JSON files in my lake, which is fairly easy. I'm telling it to read it as text. So I'm making a new data frame that's just saying, well, actually go whichever file I've chosen. Actually, you can't see that at the end. So the schema location, I've got a string. I've included these curly brackets in there. Then I've done .format.filename. And what that will do, it will just go through, and if it sees those braces, it'll replace it with that variable. So I'm injecting the name of the table that I'm using into that path. So it won't be AdventureWorks /SalesLT /brackets. It'll just replace that with product categories, the current one. So it's just a string builder. I'm building up a string to tell it the exact place to go. So it's going to that location. I'm pulling out the first row in there, which is kind of a dirty little bit of JSON, loading that and converting it into this thing called struct type. So struct type is how it's actually doing those structures. If I show you in that original one that we had when I had my hard-coded schema. So this is the actual structure type the data frame needs. So it's a struct type with a list of struct fields in there. So the code I'm running in the other one is taking a JSON file that is just looks a bit like this. So it's a flat bit of JSON that I'm just saying name, type, name, type, name, type. I'm passing that into a function that's going to change it into that format of struct type, struct field, all that kind of stuff. Again, it's only because I'm using JSON. Normally, I keep that data in a SQL database or a Cosmos DB. I do have a proper database and look it up. I only had to do this contrived bit of JSON wrangling just for this demo this morning. So that was fun. And then I get a schema out of it. So I'm displaying that schema at the bottom. So you can see it's turned that bit of JSON into this. So struct type, product category ID, product initiative type, all that kind of stuff. So we can test it out. So that's product category. So if I change this and say, well, actually, just run for product, and then click off. So automatically, by default, if I change a widget, it'll automatically rerun the cells that are referencing that widget. And you can change that behavior. You can turn it off and say, just let me do it manually. But if I go back and rerun this thing, then instead of seeing product category ID and all that kind of stuff, we should see product. There we go. So that's no longer bringing back product categories, now bringing product ID. So based on whatever I put it in that widget at the top, it's selecting a different JSON file and then getting a different structure that I'm trying to apply. With me? Good. OK. I now need to inject it. So I'm doing the same with the data location. So I'm just saying, actually, so my data, the CSV file I'm trying to reference, do the same thing we did the schema, take this hard-coded thing and just replace, look in this folder for this CSV file by injecting the file in. So I'm just changing the string that the path is. I'm adding my corrupt record. So I'm saying take that structure and just add on an expected field called _corrupt_record. So that's so that if anything does fail to pass, I'm going to be able to recognize which ones didn't go through. And then I'm just saying, take my data frame. So my data frame, blah, 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 read, apply the schema, option mode permissive, because again, we wanted to not throw any rows, not error, bring everything through if you can. And I'm passing in that data location. So up to there, that means I can pass in any name of that table, and it will apply a structure to a data frame. And again, it's just one set of code that can do that. So if I add a new folder of data and a new structure, I don't need to deploy anything. I don't need to do a release. I don't need to do any testing. It's just all metadata driven, which is great. Speeds things up. OK, then I can do some filtering. So on my data frames, I'm saying I want a good row data frame. So make a new data frame. And this data frame is based on the old data frame. So it's from DF by selecting everything and filtering where that corrupt record's null. So preserve any records that didn't have something wrong with them. And then do the same. Second one, reject rows, preserve only the ones that did have something wrong with them. So I've essentially just taken that full set of data and just said, my good ones and my bad ones, treat them as two separate things. Then I can write them to the lake. So again, we're using Parquet, one, because it contains the structure, and because I've now validated that structure, I've now checked, is it in the right shape? I can now put it down and go, everything in there is going to be in that shape from my good rows. So I'm separating that out. Again, it's massively compressed, it's column store. It means I can do a select and say, I want columns 1 and 2, not 3 and 4, and then suddenly I don't have to read those other bits because it's stored as column data. And partitioning works nicely on it. OK, so output location, same deal. I've got a hard-coded place. I'm actually saying we'll store it in a different folder for each of the files as I go through. I'm just saying write it. So my good data frame, dot write. I'm saying overwrite mode. So if there's already a folder of Parquet data there, trash it, replace it. This is going to pick it up and just replace it entirely each time. Again, you can do append, you can build it as separate files, you can do partition switching and all that good stuff. For this demo, I'm just saying just get rid of it and replace it. And then passing it that location. So it's going to take my good rows, write it down as Parquet. And then the same for my rejected rows. So I've done a little bit of date manipulation. So I'm just saying take my current date, split it into year, month, day, hour, and minute, passing that into my folder structure. So actually, each time I run this, it's going to reject rows, and it's going to store it as just a different time span period. Just so I know, well, actually, the one that just ran, that's in its own special folder of rejected rows, so I've got some ETL lineage, I can go back and manage it. And then all I'm doing is saying we'll pass that back. So count my good rows, let's count how many rows there were from the original data frame, count them from the good data frame, count them from the rejected data frame. I'm having to do a cache on each of the good and reject ones, because that underscore corrupt underscore record doesn't exist until I've cached it, because it's a system one. It has to have passed that schema. It has to have actually done it, processed it through for that actually value to exist. And then dbutils.notebook.exit put out that data. And so you can see I get something like that out at the end. So that is now end-to-end a notebook that will take a value, evaluate it against a schema, evaluate a data set against that schema, and then spit it out, which is useful. And again, you can extend that massively. You can build more and more things out to it. On the flip side, I've got a data factory. And I just said, I've got a data factory, sorry, a Databricks notebook task in there. So I'm saying that applies to a particular Databricks notebook. In this case, Data Factory, when it's talking to Databricks, it doesn't talk to the whole workspace. It talks to a particular cluster. So you have to tell it which cluster to be running on. The big processing one, the nice cheap one, you can manage that yourself. And in my settings, I'm saying, this is the notebook I want you to run. So you can hit browse, and I get my full, I can choose nicely which is the notebook I'm trying to run from it. What it doesn't do currently is automatically work out what parameters are expected. So it doesn't know which widgets I need. So I've had to manually tell it, you're expecting file name. So I've got a widget in that notebook called file name, Databricks, sorry, Data Factory, pass something called file name through to my Databricks notebook. And then I'm pulling that from a Data Factory variable. So inside my Data Factory, I've got some parameters. This is expecting its own parameter. It's going to take that, pass it down to my notebook, and then work end to end. So we can go add trigger, trigger now. Let's run this for product, fine. So if I run that, so that is going to go and talk to Databricks, say, is your cluster turned on first? If not, it's going to turn it on. It's going to find that notebook, pass that variable through, do that end to end, and then I should receive a nice output. Again, will it work? We will see. I might show you the one that worked earlier. So the kind of thing we're expecting. So the actual Databricks integration is super nice in Data Factory, because I can see this activity. I can see the outputs. So I get a link to Databricks, which will actually show me the full state for that notebook on a cell-by-cell basis. And I get my little run output. So because I had that Databricks.exit bit at the end, I chose what I wanted to pass back. So I now know can go and do some logging, can react based on how many rows processed, how many rejected, how many failed. It's like, nice, good. And I've got one ETL process to do that. So again, if someone comes to me and says, I've landed some more data in the lake, can you add it so every day it's going to validate that structure? I go, yes, and add a line to my metadata. I don't go and do a deployment and a release and all that kind of stuff. It's all about agility and speed. Okay, cool. So that is the demo of Do. Let's crack on. How are we doing? We've got 20 minutes? Yeah? Nice. Good. Okay, so why would we do this? What is the whole point of all these shenanigans and Python code and complication? And again, agility, speed is what I'm after. So old days, this is what we're doing. So every single different data set, I would have to build an SSIS package for. I'd have to build that package, get the metadata right, build a data flow, add that to my master schedule, test everything. Because I've changed my master schedule, I need to regression test the entire damn thing, eventually deploy everything and support everything, which is a lot of work. And then there's been this, obviously, a massive surge in people saying, well, just DevOps everything. Build release pipelines, have it automated so I can build something, hit go, and it'll deploy it. And yes, that speeds things up, but I still have to design it and build it. And I still have to support it once it's live. So even if I've got like a massive thing, so every time I change an SSIS package, it deploys it and it gets it live straight away. If something breaks, I've still got several thousand SSIS packages to look after. My code footprint is massive. So the kind of reason why we're doing this kind of thing is I need to build, for a new release of data, I need to get the metadata in there. And I'm just supporting that one thing. And yes, that one thing is more complicated. I've got those different cells of script to look after. But looking after one slightly complicated thing compared to looking after several thousand things, it's a balancing act of how you want to work. So for me, the benefit of agility and speed and everything that you get to from doing that stuff massively outweighs the, I need to learn a bit of Python to do that stuff. Okay? All right, so questions from Cameron. We had a couple of things that came up earlier. How do you size a cluster is a big, dirty question. So we're going to have a bit of a look at that. Best way to manage metadata en masse? Again, for me, that is just build it into a separate metadata store, but we can have a bit of a look at it, and I can try and explain Databricks Delta. Or we can talk a bit more about what happens under the hood in terms of Spark internals. So cluster sizing, or what's actually happening when you hit go and execute something. Cluster sizing? What's happening under the hood? Okay, what's happening under the hood? Fine. A note on the cluster sizing then, just to put it aside. YouTube channel. We did a thing called the month of Azure Databricks, and I put out a little 5-minute video every day for a month that almost killed me. But if you Google for advancing analytics, there's one on how do you size a cluster that talks about how you size a cluster. So actually, yeah, skip that, Google that, and you'll be able to do it. Okay, so I do have some horrendous internal slides that are all hidden that I'm going to unhide. We go. Okay. Working. Okay, so we talked a little bit about that. So we've got those data frames, and again, that's doing RDDs under the hood. What an RDD is. Mention a little bit. So firstly, files that are in a data lake are not necessarily a single file. It takes a little while to get your head around. So a data lake is based on Hadoop distributed file system. It is already a whole load of different files. So if you load a CSV file onto ADLS Gen 2, under the hood it takes that file and it splits it up into lots of little chunks called extents. So if I've got like a 2 gig CSV file and I load it up, that doesn't keep it as one file. It looks like one file to me. I'll go in the browser and I just see a CSV file and I'm like, cool. Under the hood, that takes it up, just a copy, just 3 copies of it on different disks. And actually, that one file, I can access different chunks of it in parallel. So one file is already many files to me. And when it brings it into context in the Spark server on my different workers, it might change the context of that. So even though maybe it had 6 chunks when it was on disk, it might now have 12 chunks just because of how it read it and how those workers were working, how many slots were free on those individual workers. But it's always doing that. Whenever you're loading data into your Spark cluster, it's going to change the number of chunks it's got that. And each of those chunks is called an RDD, a resilient distributed data set. So you see things like this. So I've got my one CSV file. Once I've loaded it into memory inside the Spark UI, you can say, well, what have you actually stored there? And you can see the breakdown of blocks. So be aware, if you do have a data frame and you hit cache, and then you can go and look on your actual Spark UI and say, well, what's in memory? In fact, we can go and do that. We can go and have a look. Because I did do some caching. So over here, if I go to my cluster and just go to the Spark UI, that opens up a whole new page so I can go and see what's going on my cluster. So in storage, that'll be anything that I've hit cache on. Any data frames that I've done cache, that means it's persisted in memory across my different workers. So I've got a couple of different things that are currently cached. Say, how many partitions was it? How many chunks did it do it up into? Now, because these are fairly small ones, it's done it as actually one partition. If I apply any SQL transformations, so if I actually like sort of wrote a SQL saying, take this, group it by default, the number of partitions is 200. So if you've got a really small data set and you write some SQL on it, it might just change how many chunks it's keeping it from 1 to 200. And, and over-partitioning is a performance problem. So one of the big, deep, how do I optimize my queries is having a look at each stage, how many partitions is it turning into? And you can get really deep in terms of looking at kind of trying to understand how many different partitions you're working with and why it's doing that. But you can control it. So in your data frame, one of the transformations you can do is repartition, coalesce. There's different ways of saying, I want you to turn into 10 partitions, or 200 partitions, or 5. And so you can force it to manage parallelism as you go. Okay. Again, you can do this across lots of different files, but we know that. That's fine. What's happening when we execute it? Let's do a quick thing. So I've got my Spark cluster, I've got my driver, I've got my different workers, and I've got my one CSV file, but that's held as separate different extents on disk. So I'll write some Python. That'll get passed by the driver. So the driver's going to work out what to do, pass tasks down to the different executors. Now it'll work out how many slots it needs. So it's looking and going, well, actually, I only need 2 slots. Then it'll only use 2 slots on the different workers. It's not always going to use everything. It depends how much data there is, how many extents you're trying to query. It's going to work out how many chunks of parallelism do I need, and then use that amount. So if you've got kind of a cluster you're trying to share between multiple people, then they're going to be using different numbers of slots at different times, even through a single query. Because you might be saying, well, read all the data. That's going to have lots of slots. Then aggregate it into a single file, and that'll have to use a single slot. So you've got different, it's like sort of a little hourglass of how many slots you're using at any one time. So it passes that data down to your workers. Your workers will each individually go and query the data. So again, you've got a nice separation in that the workers can work in isolation. They'll pull the data up into memory, into those RDD blocks, again, using the amount of memory that you've got. And then it'll aggregate it up, and it'll use workers to do that aggregation. So if you're trying to say, well, just return me the count, then each of the workers will get the count of the own data that they've got. And then it'll pass all of those results to a worker to add up all the different counts, and then it'll pass it back to the driver. So it's not necessarily the driver doing that all aggregation, which is kind of SQL data warehouse, that a lot of that would be the driver, whereas Databricks Spark tends to be one of the workers doing that work. And it'll work out those different steps it should go through. And it passes it back to you. And I mentioned this earlier, so Spark is inherently lazy. So if we've got something like this, and we're saying loads of different transformations to do, and the old school Hadoop way, so traditional MapReduce, if we're doing all these different things, saying filter my data, add a column, do this, do that, do a window function, between each of those steps, it's writing it back to disk. So you're pulling it up, doing some work across multiple machines, write it back to disk. Pull it up, back to disk, pull it up, back to disk, and it's kind of that back and forth. And obviously that takes time. You're doing each of these jobs in serial. Spark does it in memory. So as you're passing through each of these ones, it's kind of like each of the data sets would be in memory, but even that is slow. And that was too slow kind of when they were originally doing it. So actually, it evaluates all of the transformations and says, what's the most logical, quickest way for me to do this? So it has a thing called the Catalyst engine, a little bit like the SQL Query Optimizer. So if I've given it a ton of different transformations to do, I need to add these columns, filter this, get rid of that column, do all this kind of stuff. Again, it's not doing it when I'm lining those up. It's only when I say display the data or write the data, it'll go back up that DAG, so my list of different transformations, and work out what's the smartest way to do it, what's the fewest number of steps I can do it, what's the lowest physical cost of execution. So it has that query optimizer built into it. And again, it doesn't do that at the RDD layer. So if you're writing manual RDD code in your Scala, you have to design the optimization yourself. If you're using it, data frames or the SQL API, it'll do this. Every time you hit go, it'll go back, work out what's the smartest way to execute it, and run it that way. So Spark is lazy in that it doesn't do anything until it has to, but it's also smart in terms of it'll do it in the fastest physically best way possible. Okay, that was all I had on Spark internal. Any questions about how that works? Is that all right? Kind of make sense? 10 minutes? Cool. Direct acyclic graph. I can never say it. Essentially, a series of directed transformations or events. It's a graph. Okay, so other bits that we can have a look see at. Sorry, one more question at the back? No? Yeah. Yeah, absolutely. And there are sometimes it will do another thing. And there's one we're dealing with for a client at the moment where the order that they join table massively changes performance. So if they start with a small table, join it to a small table, join it to a small table, and join to a massive table, it takes about 20 seconds. If they do it the other way around, take a large table, join it to a small table, to a small table, to a small table, it takes 20 minutes. And it's just a massive difference because it doesn't always, so that DAG, it can't always change the ordering. It'll think, oh no, there must be a reason they started with that table and want to join that. So it won't always do things, you sometimes do have to do things in a different order, depending on how it thinks you're trying to do stuff. So it's not magic. Yeah. Yeah, it's kind of a look at the performance optimizer, see what it's doing, going, oh, it's taking the large table and joining that each time. Yeah, that's not good. Let's do it a different way. Okay. So what other sections did I have? Okay, so I guess Delta is the question. So I don't have any slides on Delta to hand. So Databricks Delta it's a new thing that Databricks implemented, and it's like a special Parquet data frame. So data is still stored in a Parquet format, but it adds this wrapper around it that allows you to do ACID transactions. It's essentially a transaction log, and it has some really, really neat things you can do. So one, you can do things like merge, and that's like unheard of in the SQL world. I can say, here's a data frame, merge it into my Delta table, and it'll take care of inserts and updates, and it'll do an upsert for me because it's got the translog and it can work out what's there. It's got a log of what's been inserted previously. You can do temporal queries. So I can say, well, actually, query this as of last week, not of currently, because it has a rolling translog. And it can change schema. So actually, I can say, well, my data frame's now got this extra column, and it'll kind of dummy it for the previous data that didn't have that column, and allow me to roll back in those ones, going, can I query it at the point when it did have that data? So schema evolution is kind of encapsulated and wrapped up into it. There's some pros and cons to it. Obviously, it does have to store data. There's an extra data cost because it's keeping this translog alongside your data. And it's really kind of mainly accessible through Databricks. So unlike like pure vanilla Parquet where everything can read it, you can't get Data Factory to read a Delta table, for instance. I would have to do a query to Databricks to give me the data. So Delta's really good, adds a load of extra stuff in there, but you have to query that data then through Databricks, which is a limitation. But then there's other limitation. So you're keeping Parquet data. You can't currently query Parquet through Power BI, which is madness, Microsoft. So you've got to design your lake with these things in mind. So if there's an element of the data, so the kind of the middle parts of your lake, and you always access that through Databricks, then absolutely 100% Delta has a ton of good things for that. But if you're landing data that you're going to use a lot through Databricks, but also through Power BI, and also it's kind of feeding in Data Warehouse, maybe that's not the right thing. So you need kind of like throughout your lake, these different layers have this layer, it's for this purpose, we're going to access it through this way, therefore the correct file type is this one. And the majority of data we keep in the lake in Parquet. So it lands in that first layer in whatever format it comes in. Once we've validated it, we'll use Parquet because it's more standardized, it's better compressed, it's got better performance. With the limitation is people can't just grab Power BI and query that lake directly. They have to go through something else. So Delta, specialist version of Parquet, comes with a load of extra functionality, some limitations, and it's only in Databricks, but it's cool. Can I make sense? Yeah.
On the deltas, so with Parquet files, I believe you can't read from a Parquet file and then at the same time overwrite it because it relies on the data on the disk.
Yeah.
Is that in some form possible with delta? So the use case, for instance, is removal of duplicates from new data that you get in and you don't want to store duplicate records?
Yeah, so kind of Parquet has some limitations because it's compressed. So you can't like insert a row in the middle of a Parquet file. So if you're trying to change data that's there whilst reading it, then you have limitation. You generally do get rid of the old one, replace it with a new copy, and that And the other thing that you don't want to do with Parquet files, because it's column store compression, the compression is more optimized the more data you have in it. You have a thing called run length encoding, which is kind of like when it has, if it's like the same value repeated for the next 10,000 rows, it won't store 10,000 values, it'll store that value times 10,000. And suddenly the size of your data just shrinks massively. Whereas if you've got actually every single record I'm storing as a separate Parquet file, it has no compression. So the smaller the Parquet file that you create, the worse the compression, therefore you lose the benefit of Parquet. So one of the things, if you're trying to do lots of small incremental updates, and they're having like small, tiny Parquet files, then that's just rubbish and you might as well not have Parquet. One of the things that Delta does is it does have kind of a garbage collector that will go through and it'll create these little tiny Parquet files, and then it'll periodically go and clean it up. Actually say, we'll take those 20 small Parquet files and just compress them all into a single thing. Good. Fine. So yeah, there's some optimizations around that to manage the small incremental updates and streaming data into it and then going and cleaning that up. You wouldn't normally do that into a Parquet file, but because they've got the translog, they then wrap it up. So yeah, there's definitely benefits around that stuff. All right, cool. Well, that is all I had to go through today. Any other questions? Awesome. Okay, so there's a raffle outside very soon, I think, in 5 minutes. I think. Yeah. And then there's an after party in Brewdog. Yeah. Beers. Good. Thanks.